Hi, my name is John Bannon. I'm an attorney and philosopher. I want to explain how superdeterminism has been boosted by a recent European XFEL experiment. Now, when I talk about superdeterminism, I'm talking about a very unique version of superdeterminism proven by Swedish theoretical physicist Dr. Johan Hansen in 2020. You can find his proof in the peer-reviewed physics journal Physics Essays, Volume 33, Number 2, 2020. Dr. Hansen said and proved that we live in a superdeterministic, predetermined static block universe without cause and effect in physics. On August 7th, 2025, a paper was published giving the experimental results performed at the European XFEL, which stands for X-ray free electron laser facility, that showed that molecules undergo random zero-point motion even when unobserved or unmeasured. Now, you can find this report or this paper at the published journal Science, volume 389, issue 6760, pages 650 to 654, August 7th, 2025. It's entitled Imaging Collective Quantum Fluctuations of the Structure of a Complex Molecule. Now, under the Copenhagen interpretation of quantum mechanics, there is no actual definite reality for the unobserved or unmeasured because they're supposed to be in this superposition of possible states under the wave function. The XFEL experiment directly contradicts the Copenhagen interpretation of quantum mechanics. A definite quantum reality in the form of a molecule is undergoing random perturbations, um, and it's not being caused by preceding perturbations. So, in other words, the experiment is showing that the molecule that it measured must be undergoing this inherently random change in its structure. And this is an ongoing change in its structure. So it's changing from one variation of that structure or random structure to the next variation of that random structure or these perturbations, one after the other, after the other, after the other, even though they're not being observed or measured. So this challenges the Copenhagen interpretation because the Copenhagen interpretation says there is no actual real reality that's not that's there that's not being observed or measured. It's just a probability wave of these possibilities. Whereas this XFEL experiment is saying, no, that's not true. That random reality is actually real. It's a real molecule, and it's going through these perturbations through time, even though it's not being observed or measured. So that is a direct strike at the Copenhagen interpretation of quantum mechanics, proving that it's wrong. Copenhagen is wrong. Um, Now, this molecule continues to exist unobserved and unmeasured in time without the need of cause and effect in physics. And the reason for that is if you have an inherently random perturbation followed by another inherently random perturbation, because they're inherently random, that means they cannot be deterministically caused by a prior quantum state. So they have to be a series of randomly changed actual realities in this molecule, where each change is not caused by the prior perturbation or the prior change. It's just a series of these randomly changing states of this particular molecule. So that's a molecule that can exist in time without the need of cause and effect in physics. And because um, there is no superposition, because these molecules that, even though they're unobserved or unmeasured, are real nonetheless, so there's no superposition, there's no probability wave. Well, then there can't be probabilistic causation, because that only applies where there's a superposition under a wave function. The net result is you really do have an unobserved molecule undergoing actual changes, random changes in its structure through time that are not caused by anything. They simply exist. Now, um, what could do something like that? Well, the answer is Dr. Hanson's superdeterminism could do that. So you can imagine in a static block universe without cause and effect in physics, this sequence of randomly changing actual states of this molecule in a series through a static dimension of time. Doesn't require cause and effect, doesn't require probabilistic causation. So you may wonder, well, how do they know that this molecule pre-exists the measurement of it? Because the only thing you've seen is the measurement. And the answer is they can tell because they use a laser that is so quick. It's 10 femtoseconds. That because it takes that quick a laser to get a clear picture of the molecule, then that implies that the molecule must be moving very quickly, very changing its state randomly very quickly. Because you can think of it as like the camera speed of a camera's shutter. And if you're trying to take a picture of something that's moving very fast, then you need a very fast shutter speed in order to get a clear picture of it. Otherwise, you're going to get a blurred picture of it. And because in this experiment, it requires super fast 10 femtosecond shutter speed essentially to get a clear picture of the molecule, that's telling you that the molecule must be moving very fast. It must be changing in um, its configuration randomly, very quickly in time. In order to avoid a blurry picture, you need a very fast camera speed. So that indicates that it is in fact moving, and that means it must be moving pre-existing the actual measurement of it. So the experiment itself, you can read it yourself, but it essentially says that when they look at these molecules and their structure, that every time they take a picture of it, it's different. It's randomly different, which is consistent with 0-point motion. And 0-point motion is the idea that due to the laws of quantum mechanics, nothing can actually sit still, even at the quantum level. I mean, you could put it down to absolute zero and it'll still move due to the Heisenberg uncertainty principle. That's that's called 0-point motion. So these molecules are showing 0-point motion, and that must pre-exist the actual measurement, which means the molecule has to actually exist while it's not being observed in order for it to have 0-point motion. So it's telling you that um, the the quantum substratum is an actual real thing. It is not a superposition like the Copenhagen interpretation says. So This is a very recent experiment, and it highly supports superdeterminism and basically disproves the Copenhagen interpretation. Not only that, it also disproves the many worlds interpretation, because the many worlds interpretation relies on a collapse of the wave function in order to posit the existence of a branching multiverse of many worlds. Well, if you don't have a collapsing wave function, uh, then you don't need a many worlds interpretation. So this is strong, scientifically verified support for Dr. Hansen's version of superdeterminism. I'll give you a second to read the board. Okay, I hope you learned something and you become a believer in Dr. Hansen's superdeterminism because it's true.